www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, so let's get started. And today is lecture 6, and this is a continuation of the energy band and its properties. And the idea is, if you remember, that we are in the process of calculating the total number of electrons that can respond to an electric field so that we can calculate current. The number of atoms multiplied by the number of electrons per atom didn't give us the right result in terms of conductivity. And we're trying to find what fraction of the electrons are actually moving in response to an electric field. And we are already making headway towards that goal, because we have seen that by solving the Schrodinger equation in a periodic potential, we find that the electrons do not sit everywhere. Some of them sit at a very low level, and they have certain properties separated by band gaps, and then we have a series of these levels. And what we want to explore is that all looked very complicated, whether there is a summarized version of that information that we can use later on. So the energy bands are essentially the solution of the Schrodinger equation that tells us at what energy and what wave vector levels the electrons can sit. So today we'll continue on the properties of the electronic bands. We'll also talk about this notion of an EK diagram and constant energy surfaces before concluding. So let's talk about this a little bit. Again, on the left-hand side, you remember that this is the solution of the Schrodinger equation in a periodic potential. We have y-axis is energy, and the plus and minus k are the wave vectors where the electrons can sit. Do you remember that this came from the periodic boundary condition when we bring the string together, the first atom connected to the last atom? Only certain k's are available. Plus k moves one direction in the chain, and the negative k goes the other way. Now let's think about this, about when an electron sits in these bands, how would they behave? I have shown here something called an EF, which is Fermi level. Now, at this point, you don't need to know what it means, but let's say it is some level above which there are no electrons, and below which all the electrons sit there. So, for example, now in this case, what would be the current for such a band? Now, the first current associated with the purple band, we are calling it J33 because it's sort of the third band from the bottom. And you can immediately see that all the electrons should have a minus q, and I must sum up over all the velocity, because charge multiplied by velocity gives me the current. But here, I don't have any electron. So, of course, I do not have any current, right? Because there's nothing here to carry the current. So I have it 0. That's no problem. What is more surprising, however, that electrons on the bottom, on band 2 and band 1, also carry no current. That's strange, because there are lots of electrons, you see. So in principle, they could have carried current. And the reason they don't carry current is because of this. For example, if you focus on the first band, I'm again summing up of all the electrons carrying different amount of current because they are moving with different velocity. But when I do, I quickly realize that I have equal number of positively going electrons with plus k and negatively going electrons. And so therefore, although each one of them is carrying current, the sum of them is 0. It is like going from Chicago to Lafayette. Let's say both lanes have cars going in the opposite direction, but one way, there is two ways there could be no net flux going from one point to another. If there is no cars, which is band 3, or if there are equal number of cars going in the opposite direction, in that case, it is again zero current. Two quick points. Now, this argument requires the number of states that I have in the plus k lane and the number of states I have in the minus k lane, they are exactly the same. Now, for all Bravais lattices, which has inversion symmetry, that if you put a mirror and reflect it, it remains exactly the same. In those cases, this will always be the case, that the same number of plus and minus k state. This is not generally true. Second, you could argue, couldn't they simply, when they move, couldn't they just sort of pile up on top of each other? You know, two electrons occupying the same state. That way you could have a current. But of course, because the Pauli exclusion principle, and these electrons are fermions, therefore, unless one vacates the space, the other one cannot move in. So therefore, in this case, there would be no net current, although there are lots of electrons. Now, what about partially filled state? Let's say you have a band, you make the temperature a little bit higher so that some of the electrons which are sitting in band 2 goes up in band 3. Now, in this case, even in the beginning, it might look like that there is no net current. You see the number on the rate side, on the positive, and that on the negative side, they're again exactly the same. So in principle, there shouldn't be any current. And the same is true for blue. Except that when you apply an electric field, what will happen? Let's focus on the red points. Because the electric field is in the positive direction, and the electron has a negative charge and a negative effective mass, positive effective mass, in that case, electrons will be moving opposite to the direction of the electric field. In this case, you have more electrons going to the negative side compared to that of the positive side, you can easily see, and as a result, the current will no longer be zero. And so that's no longer zero. What precise value it is, we will calculate later on. But the point is that in this case, on a partially filled band, the current will not be zero. Now let's focus on the blue one. What happens in the blue one is, again, of course, if you apply an electric field, but remember, these are electrons, which is fine, minus q charge, but these have negative effective mass, so they will move in the opposite direction. And as a result, when the electrons in the valence band, they move in the opposite direction, correspondingly, there will be an asymmetry between plus state and the negative state, minus state, and together, once again, there will be a net current. But there is a very nice way to think about this, and that's something called a hole. And let me discuss that. How many states do I have per band? Do you remember? This is the total number of atoms that I have in a crystal, right? Now, that could be millions of atoms, let's say, or a billion of atoms in a string. So therefore, the number of blue points I have shown is on the order of a billion, let's say, in a one-dimensional chain, although I show here only 5 or 6. Now, if I have a billion, summing them all up to get a current is very difficult. So therefore, I could do the following. What I could do is that instead of summing over them all, I could partition them. I could sum them over all the states there are, regardless of whether they are full or not, and that's the field or not. That's the first term. See, below the sum I say all. It means all state regardless whether they are full. And then I have added something, because of course the first term is negative. I have overcounted because some of the states, there were not any electron. I shouldn't count them. So I have taken them out in the second state, but this time I have added them as empty. Now the first term you say, which has the sum, below the sum there's all, in this case there are the same number of plus states and same number of minus states, inversion symmetry, Bredouin zone, and all the Bravais lattices and all that. and as a result, the first term will go to 0. You see? And therefore, the second term remains. And the second term says that when I want to calculate current in a field band which has a negative curvature or the negative effective mass, then the best way to describe them is to focus on the ones that are empty. Because then you see there are millions of them, so I don't sum them all. There are few empty states. I focus on them. I assign a plus q charge. Look at that I have, instead of a minus q over L, I have a plus q over L left. So I assign a plus charge and let the electron move, let the holes move, in this case, the empty spaces move in the same direction as the electron with plus velocity. And so this way I can again calculate the total current, and this way of viewing things are called the holes. These particles, fictitious particles that I'm thinking about, these are called holes or empty states. Now things are a little bit more subtle, but let me give you an analogy, at least for this course. I think that should be sufficient. Assume, and this is an example Shockley originally gave, that assume that you are on the top of a building and you are seeing a few cars from the top of a building on the parking lot, and the cars are black and the background parking lot is white. Now, when there are few black cars moving in one direction and another, you're taking pictures from the top, you will see a few black points moving around in the white background. However, assume that the parking lot is essentially all filled with cars. Now, there are few spots left, and those will look as if it's white. There are white spots from the top. Now, when the electrons are moving in a particular direction, or the cars are moving in a particular direction, it will be a bunch of black space with a few white spots moving. Focusing on the white spots is like thinking about holes. And you can see the same direction electron goes is the same direction the white space goes, because white space cannot move. It's moving because the electrons are moving, or because the black cars are moving. So that conceptual framework gives you this idea that why the charge is positive and why they move in the same direction as the electrons do. The empty states move in the same direction as the electrons do. Now, this is a very important concept, and I will hope that you'll spend some time thinking about it clearly. Now, one thing I want to point out that about this effective mass is effective mass is not equal to the free electron mass. Effective mass sort of encapsulates the information about the lattice and where the electron is in a given lattice at a given energy. Because the electrons, had it been in the free space, it is always have a net value of m naught, 9.1 10 to the power minus 31, let's say. Of course, in each of these bands, we have already seen the effective mass is variable, sometimes is positive, sometimes negative, sometimes 0, all sorts of complicated things, right? It is because at each band, the way the electron responds to the electric field is not the same. When it is sitting deep in the potential, of course, you apply a field, it cannot go anywhere. So its mass is very heavy. When you go up in energy, it moves very easily from atom to atom. So its mass is low. So in some way, it retains the information about the crystal within this effective mass. Now, one thing is that if it's varying all over the place, it wouldn't have been a very useful concept, except that you realize that although it varies, let's say corresponding to the red band, this is the effective mass, or 1 over. For the blue, which is the whole band, it goes the negative, and similarly for the green and the other one, third and the fourth one. Now, first thing you realize that, well, the red one doesn't matter because this is full, way below the Fermi level, carries no current. I don't care about that effective mass anyway. Second one is that way on the top, I don't have any electron. So I don't worry about that one either because it's not participating in the conduction process. The ones that I worry about are only a few, only 2 or 3 or 4. For example, in this case, we only worry about, let's say, the green and the blue one, where the electrons can actually move. But even in that case, we worry about only towards the bottom, a few little states towards the bottom. And you can see the corresponding region where I plot 1 over m star, in that little part of k, it is approximately a constant. So therefore, in the top and in the bottom region, this is approximately a constant, and as a result, you can say that those bands are characterized by that mass. Of course, a given band doesn't have a complete one single mass, but for practical purposes, for calculating the current, when they are sitting on the bottom of a band, I can represent each band with effective mass. Okay, so that's all I had to say about effective masses and bands. Now we will want to discuss a few other things. Again, a preparatory information for the next lecture, where we'll talk about real crystals and how to think about it. But the first point I want to discuss is something called a Brillouin zone. By the way, one quick point, let me mention, which I didn't do in the previous slide, was that you remember that there was a place where the mass of an electron went to 0. Do you remember? Started from positive, went to 0, and then went to negative. Now, what does it mean? Negative effective mass, we just talked in the context of a hole, that how to convert it to a positive mass and a positive charge. We just did. Now, what does it mean when you have a mass equals 0, right? Or the current or 1 over m star equals 0. Well, it simply means that when you apply a field, you cannot accelerate it, right? That's what it means. But that does not mean that the electron will sit there. In fact, electron is moving with a certain velocity when it has a positive mass, let's say, and then when it reaches that point, its velocity will not change because it cannot be accelerated. That doesn't mean its velocity has gone to 0. It will cross that point in k and then continue on and respond to the field. So unless one purposely put an electron in that state itself, which is never possible, then in that case, the 0 effective mass does not mean there is no electronic transport. All right, so let's talk about EK diagram and constant energy surfaces. Now, one thing you noticed when we solved all these problems, that all the bands are finite in size. Here I have shown here in green region. Towards the bottom, the bands are very narrow, high effective mass. Electrons don't go from one side to another very easily. They are filled on both sides anyway, so it doesn't really matter. And as you go up, the size of the bands changes. Fine. But the first thing you notice in this solution, that the solution goes from plus k to minus k, not on arbitrary values, but only over pi over p. P is the lattice spacing, and minus pi over p. That is what the solution is. And what the solution is, that's the next point. But first is that the solution cannot go beyond that point. So that's called a Brillouin zone, and you can see that it could be constructed this way. On the right-hand side, I have shown the position of the real atoms, real space atoms with circles, and they are spaced at p. P is the spacing, not momentum, remember. I could do this following, let's say just by construction, that because I have p, I could take that p and make this minus 2 pi over p, 4 pi over p, just by construction. I could calculate a set of numbers, 2 pi over p, 4 pi over p, 6 pi over p, and populate the plus side. And remember that this is 1 over a real space dimension, p, so it has a dimension of a wave vector. And similarly, I could create a series of points with minus 2 pi over p, minus 4 pi over p, and go along. And so it's like a k space or wave vector space lattice. Now you see, if I take halfway in between, starting from 0, connect it 2 pi over p and minus 2 pi over p, sort of take a vertical cut, that green region has the edges at plus pi over p and minus pi over p, right? Now notice that the solution space I have on the left-hand side is exactly the same. So although I have not solved the Schrodinger equation at all, right? I haven't done any equation, but I already know just by this construction that where my solutions will be, where I'll have to fish for the solutions. Now, if this is the case in 1D, then what happens in multiple dimension? Well, it turns out that there is a very simple algorithm to find where the solution is. The actual solution will come a little bit later. And these are the formulas by which you can use to calculate this. Now, you will do it in homework, so you will understand this in great detail when you do it for the homework. But the point is that there is this recipe that if you have a three-dimensional unit cell with sides A, B, and C, then you can correspondingly create an inverse lattice or a K-space lattice by finding the formula for Kx, Ky, and Kz. These are the unit cells, lattice for the unit cells in the reciprocal space. And I'll give you an example. And then you can use the Wigner-Seitz algorithm, but this time for the inverse space to show where the solutions would lie. You see? So let me give you an example. It will become very clear. Nothing complicated here. Do you remember this particular picture where we had in a real space a lattice with lattice constants A and B, not necessarily perpendicular to each other? We chose a central point, connected all the neighbors, and then took a perpendicular bisector for each one of the points and looked at the enclosed volume, the smallest enclosed volume, and that was the unit cell. You remember this, right? Now, the proposal in the previous slide said that in order to create a corresponding lattice space in the inverse reciprocal lattice, what I should do is the following. This is a two-dimensional space. Therefore, I have in the third dimension, I could say that I have a unit vector of size 1. Right? So therefore, instead of C, I have just put Z caret. But other than that, you can see the first one is Kx 2 pi B cross Z caret and correspondingly A dot B. And when you simplify, you see immediately that the result would be essentially 2 pi over A. And similarly for Ky, do you see that it essentially will be 2 pi over B, right, in this particular case? So if you have that, you could correspondingly create an inverse lattice of points where you start with a central point and then create the points 2 pi over A, 4 pi over A, 6 pi over A, keep going in that direction. Along the y direction, Ky direction, you start 2 pi over B, 4 pi over B. Now you have the two axes and fill up the whole space by these points. Again, this time use the Wigner-Seitz algorithm on this figure. And when you do, same formula, same procedure, same mechanism. When you do, this would be called the Brillouin zone. And this is where, within this space of Kx and Ky, all the solutions of the Schrodinger equation must lie. This is where the electron, these are the only wave vectors the electrons can have when they propagate through the crystal. Right? Okay. So in that discussion, let me quickly show how the one-dimensional one would look like. You see, started with P. I make the inverse lattice at 2 pi over P. I do the Wigner-Seitz algorithm, cut it in half, and I have the corresponding EK diagram. You can see pi over P and minus pi over P. Now, one thing I want to point out here, these are the solutions. Somehow I have calculated the solution of the Schrodinger equation. Now, one thing I want to point out here, very important, which is I shouldn't really have plotted 0 to minus pi over P. Why? Because you see, this is exactly the same. 0 to plus pi over P, whatever solution I have. If I just mirrored it, then I could have gotten all the solution. So I'm really unnecessarily plotting the reverse side. And anytime again you have inversion symmetry, this will always be the case. The solution in plus K will exactly be the same as the solution of minus K. So why waste space and trees in order to draw another half of the diagram, right? So we shouldn't, most of the time you'll see, we'll just say 0 to pi over 2 and assume that my 0 to minus pi over 2 is exactly the same. Okay? Now, let's think about 2D, which is a little bit more complicated, but we're going to get to the 3D, what we are really interested. Now, do you see in 2D, our Brillouin zone would look something like this. Assume that I have one of the 5 Breville lattices. Do you remember? We had in 2D 5, and one of them was A not equal to B, and the angle was 90 degrees. Let's say I have taken one of those. And then my rule is that I should populate the inverse space as 2 pi over A, 4 pi over A, and so on and so forth, and then cut it in half to define the Brillouin zone. And therefore, I have pi over A to minus pi over A, and pi over B on the y-axis in the blue axis, and minus pi over B. You see, this is where the solution will be. I don't know the solution, but this is where the solution will be. Now, the solutions, of course, would look a little bit more complicated, and it might look something like this. Previously, remember, I had these 4 bands, and I had just one axis, plus kx or minus kx. Now, in this case, of course, I will have a 3-dimensional thing. It's like energy is like a pole, and these cups are hanging from the pole. And if I had 4 bands, how many caps do I have? I have 4 caps hanging on the pole. Now, the point is that drawing such a thing is easy on a PowerPoint, not even easy on PowerPoint, but it's very difficult if you had to do it every day and draw it this way, which is very difficult. And it's difficult to read off information also. So many times what people will do is the following. Instead of really plotting the whole thing, they'll plot this 3-dimensional information on a 2-dimensional plane. It is like a weather temperature map in the newspaper. You see, let's say at different places, the temperature is different. They put a contour map, right? They put a contour map, that type of idea, that representing 3-dimensional information in 2-dimensional plane. How do I do that? So one is that, let's say along the red axis, I make a cut. If I do a cut, then the kx axis goes from 0 to pi over A. Do you remember? And I have the corresponding surface shown here is also with a red line corresponding to that cut in the cup, right? And I have only plotted 0 to pi over A because my 0 to minus pi over A is exactly the same. So I haven't plotted it. One panel is enough. Now, if I wanted it along ky direction, what should I do? Well, I should cut the cup vertically with a knife along the y direction. Now, the y direction goes from 0 to pi over b and 0 to minus pi over b, again symmetric. So I will just put half of them. I have put them in half of them, and then in order to look nice, I have made the 0 to pi over b looking the other side. Of course, you could do it in any way you want. These are just 2 panels of the cut. Now, of course, these are not only 2 panels. If you really wanted to represent the whole cup, you should have taken a cut at 5-degree angle maybe. And that way, you'd have maybe, you have 360 degrees, right? You have 72 cuts, and you could plot out, not 72, half of them are exactly the same. So maybe 36 cuts, or no, 18 cuts, and you could have 18 panels. And from that 18 panels, you could always reconstruct the cup, you see. So these will be called the EK diagram because it tells you the energy versus wave vector along any particular cut, you see. Okay. Now, 2D isn't that bad, but 3D will be a little bit more difficult, you will see. But if you understand how the procedure of doing things, it will be a piece of cake, you see. Now, this is not the only way we could represent this information. We could also represent the information in a slightly different way. So that's the EK diagram. Now we could represent it this way also. Instead of taking a vertical cut, taking a knife and cutting through the cups vertically, I could also have the information and cut horizontally. If I take a horizontal cut at any energy E and then look at the ring at which it has been cut, I could have shown that you can see on the bottom right hand side, the solution space is again kx and ky, pi over a to pi over b, but this ring with a constant energy E1 could be represented by this magenta circle. Now, it need not be circle. It could be anything. Whatever it is at that energy, I could cut it. Now, in order to represent this one cut is not sufficient, right? I will start with E equals 0, energy equals 0, and I will have to take horizontal slices, as many as I want, all the way to the top. But remember what I said a few minutes ago, that only a few bands take part in conduction. So if you are an electrical engineer thinking about just carrier transport, you will just worry about cuts in the conduction band and in the valence band. And the ones that are too much below, they don't carry current. On the very top, they don't carry current. So we'll not worry about those constant energy surfaces. But of course, spectroscopists and others, they might want the information for those ones also. Remember the photoelectric experiment where they pump electrons from deep in the valence band all the way out. In that case, you need that information. For us, for the time being, we don't need that. You can, by the way, you could also construct this EK diagram, for this constant energy diagram, also from the EK diagram also. And the way you'll do it, you'll take a particular energy and see at what points in the red and the blue they cut, and whatever point they cut, you will, in the corresponding axis to the right, you'll pick that point. In this case, you have just 2 panels, so therefore on the constant energy surface you can just have 2 points. But if you had the 18 panel, if somebody laid down the 18 panel, by having a constant energy cut, you could instead construct from this 2-dimensional plot this particular constant energy surfaces. And this we will often do. We will not really picture this 3-dimensional complicated thing at all. We'll always go back from EK diagram to constant energy surfaces back and forth without ever bringing in the complicated 3-dimensional one, you see. So you should be very comfortable about how to draw it, because I will ask you to draw this repeatedly on various occasions. So that's it for as we start our discussion in the next class for actual 3D. I think we have all the preparatory information for that. And very quickly, what we saw that the electrons only sits in a given states and with a certain value of k. And what are those values of k? 2 pi divided by np. N is the number of atoms. So that is how far they are spaced by, and they sit in a given state. The second thing is, at a given band, right, in the given band, the electrons, the number of states is equal to the number of atoms, because that is how many people came to the party, bringing in their own food. And so therefore, in each band, they must have the same number. Actually, the number of states is actually even, because whatever the number, let's say 11 atoms came together to form a solid. Now, of course, each state, there is 2 spin up and spin down, and that we'll discuss later. So therefore, it is always number of state is 2n. And so the number of states in a given band is always even if you count for the spins. This is something important. We'll talk about the implication maybe in a few classes down. Effective mass, said that's not a fundamental concept, and there may be systems where the effective mass cannot be defined properly. Do you remember that the graphene relationship? You should also convince yourself that in that case, how to think about carrier transport in those cases, and how to think about the negative effective mass or zero effective mass in those cases. Okay. The third point was only a few bands contribute. Conduction and valence band, partially empty or partially full. And then finally, the most of the practical problems actually can only be solved numerically. That's something important, because we did these things analytically just to get started, but numerical solutions is what we'll need.